people are eager to learn as per as the interest of the student, those for the hardware, embedded system and these hardware related programming, Proteus, simulations, understanding various IDE. Even student from second year itself, if it is there and is belonging to the branch of electronics and telecommunication, it is very important for them to understand how to find the architecture, instruction set, how to understand the microcontroller, microprocessor, what is the difference between them both, and the programming of that one as interfacing of all the sensors and all the components to these controllers. So as we are in the particular domain where this electronics plays the role everywhere, right from the household to the defense sector that we are all observing per today, what's happening globally, and how these particular electronic equipments, the warfares, the drones, okay, the radars, everything is there. So sensors are there, and controllers and processors are there. So considering all these things, the importance is there and is very demanding thing as an embedded programmer in the industry. Everyone interested in this Java and other type of the softwares, but even though the embedded system is embedded with AI, embedded with the Java, okay, so it's a word of quantum computing. The quantum processors will be there, but even though we have to first understand the fundamentals, how a 8051, 89C51, or if you're going for the ARM controllers. Okay, so with the interest and the key interest of the every student in this particular one will lead you to work on much more projects, and it will definitely give you the satisfaction once you feel complete the projects. Okay, getting it? So today we will start for our internship program. It will be for the per 2 hours per day and almost up to the 30th June maximum. Based on your response and the requirements also, we will try to work on it. It will benefit you for developing the projects, for understanding the programming aspects, the simulations, and very specifically for this program, we have added CAN interface, CAN protocol, which basically never get completed in various type of the workshops, and it necessary as far as the automotive electronics is considered. And we know that ECU, electronic card unit, it is present in the vehicles, cars, right? So how to do the programming of ECU, what is the CAN interface, how the all sensors data has been taken from the vehicle. So like that way the CAN interface protocol is also has been added. Getting it?
Yes, sir.
Okay. So we have the various resource persons for this particular internship program. They will share their experience from the industry. They will focus and will guide you that what to study and what is the need of an industry. And very important that we have the Dr. Rajesh sir. He is main here the resource person to make you aware about all this particular content, and the supportive resource persons will focus on your career also and the requirement of the globals also. So we have make blended version of this one. We also try to add our alumni, those already working as embedded managers in industry from last 6 7 years. So we are trying to pull them for the interaction session of 10 or 15 minutes within this internship program. Like that, various industry persons, academicians will make you aware about this particular domain. Okay, so we welcome today's resource person, Dr. Rajesh sir.
Yes, sir. Thank you,
Uh,
sir.
Yeah. So as a profile of Rajesh sir is having the very skillful things in the embedded system design. He has been doctorate with this domain, working with the one of the renowned organization and the institute, New Horizon College of Engineering, Bangalore, associated with the industry, various consultancy projects, and with particular network and a team of industry and academia around with him. So it's a very good thing that they are providing the time to us from their busy schedule. That's why I said 2 hours are very important every day. Without wasting the time, every student who has enrolled and paid must join at a right time so that there will not be loss on their side. Is it okay? So initially all students should switch on their camera. These are my instructions. Because you people are in the vacation holidays, let's see your face. Huh? You should be wake up in early morning, right? आदतें बिगड़ी नहीं है अभी. चलो, no problem. It's a warm welcome to all of you as a student and learner. And basically, without wasting time, I would like to hand over to the session to Dr. Rajesh.
Yes, sir. Thank you very much for the nice
Yes, sir.
introduction, sir. So, welcome, students. So, I'll be expecting some sort of interactive sessions before I start this. Okay. Yeah. So, straight away, we'll just dive into this. Just confirm me whether my screen is visible or not for everyone.
You are visible. Whatever that you share, we'll check it only
Yes, sir.
as the screen. Yeah. Yes, sir. Visible, sir. No issue.
Okay, fine. Just let me just change that. Right. Right. So this is an actually scheduled for 20 hours. Okay, so each and every day or each and every session. Okay, so we are going to learn something new about this embedded system. Okay, so whether it can be right from the scratch, okay, we are going to do till the latest processor and whatever the tools associated with that. Okay, so the first thing what we get into our mind when we call it as an embedded system is, so I want some answer from the students. Anyone who can just give some answer. What is mean by an, what do you understand by an embedded system? Any student. So if you're feeling, if you're unable to just give your voice, you can just drop the message answer in your chat box. That will also.
Lalit, are you getting the voice clearly?
Yes, sir.
Okay.
Okay. So this session should be interactive. It should not be one side. Your money is valuable for us, right? So by that way, the interactions should be there properly. So the first question is that what do you understand from the embedded system?
So embedded system is a system in which we'll use different kind of microcontrollers and the controllers. By them, we'll give command to them to perform a such kind of work which is useful for our
Okay, right. So here I go with this. So embedded system, usually we call them as a automation system. Simple, in one word. Generally, we have to tell. So technically, we have several definitions. Okay, but simply an embedded system is an automated device. Okay, so just like if you take a washing machine. Okay, so it is an automated nowadays. Okay, so now what we are doing, we are taking the clothes, we are keeping the, we are putting the clothes inside that. We are just adding some washing powder or something like that, and you are going to use some timers. Okay, you are going to decide that for how much time it has to be washed. Okay, after washing, whether it has to be rinsed or not. So this type of things you are going to give as an input, isn't it? So what you are doing, your washing process has been automated with a machine. Okay, so this is what a simple embedded system generally. Okay, so what makes this embedded system? Okay, so if you see embedded system closely, okay, this embedded system consists of a hardware. Okay, and in order to work to make that hardware work automatically, we require some programming skills. Okay, which is with respect to that hardware only. It is not a general programming skills what we use for C language like that. Okay, so this programming skill should be very much specific to that hardware what we are learning. Okay, and sometimes nowadays we are just focusing on everything is IoT. So through mobile only you're going to control the washing machine. Okay, that is possible with the help of IoT. GSM technologies, everything came into picture, but IoT is the one which is uh, prominent nowadays. Okay, so you require some connectivity also. Okay, so altogether, if you want to tell what is an embedded system, an embedded system is an hardware which is activated by a software and has a capability to communicate with others. Okay, so your hardware will be there, okay, and your software will be there, and your networking will be there. So all the three parts combinedly we call them as a embedded system. Now if you see any embedded system, any automated machine, okay, that we are using nowadays, okay, consists of all these three elements. So it consists of an hardware, okay, it consists of some hard software, a programming, and then a network capability. So if you take an ATM machine, it just looks like an computer. Okay, so whatever the computer has, everything is there in the ATM machine. Okay, but it is used for a specific purpose. Okay, so now we will extend our definition of an embedded system. Okay, so an hardware, okay, which is activated by a software and has a capability to has a capability of networking, okay, for a particular or for a specific application is said to be an embedded system. So these embedded system are application specific systems. Okay, so now for this, what are the building blocks you see? Okay, so the building blocks we call them as core elements or the core components of an embedded system. Okay, so we require an hardware. Usually, this hardware is called as the brain of the embedded system. Okay, so, and this brain can be of a microcontroller and or a microprocessor. Okay, then we should have memory. Okay, so why we require memory? So in order to store the commands what we give. Okay, and also in order to execute them. Okay, so this memory, we have varieties of memories. Okay, we have RAM, we have ROM, flash memories like that. Then we have the sensors. Okay, so which will take the inputs. Okay, so which will take the inputs, right? So from which we will get the inputs, right? So it can be from the physical world or it can be from the programming also, the inputs can be. Okay, so altogether we put them as sensors. Now it goes like this. So whenever the sensor senses the data, okay, it is given to the controller. Okay, this controller is going to process it, okay, with the help of the commands which are taken from the memory. Okay, and finally it has to give the output, right? This output is done with the help of actuators. Okay, so these actuators are action based systems or action based devices. Like if you take a fan, okay, so fan is an actuator. Why? Because whenever you give electricity, it is going to rotate. Okay, so it's just like a light, okay, or LED. Whenever you're giving some electricity, it is going to illuminate we are going to illuminate it. So these are some examples of the actuators. So if you see now, we have got this four building blocks like the controller or the processor. Then we have memory. We should have a sensor. Then we will have a actuator. Now these things has to be done within a specific course of time. Let us say it has to be done with 10 milliseconds or 1 microseconds. Then the data has to be sensed, it has to be processed, and it has to come out within a span of microseconds. So if this has to be done, the data has to be very much the data has to be propagated very much fast. Okay, the data has to be converted, the data has to be converged, then the data has to be communicated to the respective devices. Okay, so for this we require certain communications. Okay, this is means within the embedded system, right? So for suppose if this has to be controlled by a remote location, then this information has to be passed through a wide service or wireless service, where we come across some communication protocols. Okay, so if you take within the embedded system, what sort of communications we are doing? Okay, so there comes certain protocols like SPI, okay, I2C, then CAN protocol. Okay, like if you take the converters like ADC, DAC converters will be there, and then in order to count the timing, we require some timers. Okay, and then we should have certain ports which can act as an plug and play, like general purpose IO we should have. So these are the peripherals that will be there. Okay, so now we understand if you this that the embedded system requires a processor, it requires the sensors. Okay, so to get the data, to process the data, we require that controller or processor, and to do the final action we require the actuators. Okay, and for memory, okay, we require for storing the data or the program, or for and peripherals we require for for the respective operation, right? So if you have UART, okay, so it is used for mainly for serial to parallel, parallel to serial communications. Okay, then SPI, okay, so serial peripheral interface. Okay, so like this, different peripherals will have different tasks of communication within the embedded system. Okay, so within the embedded system means the communication right from sensor to actuator. Okay, including memory also. So in that aspect, first we will just concentrate on the controller. Okay, so without this controller, even though if you have memory, peripherals, sensors, actuators, nothing can be done. Okay, so there should be a processor which can do it. Okay, so as we discussed, we are not going to discuss about the general purpose applications. Okay, we are very much specific about a particular application. Okay, so in that scenario, okay, so we have to be very keen in choosing the brain of the system, that is the hardware. Okay, so there are two varieties of brains. Okay, so a brain which can process all the applications just like a desktop what you have. Okay, and a brain which can do one application, one process one specific application. Okay, so that category comes under microcontrollers. So this is the basic difference between a processor and controller. Okay, so a processor is the one which will do or which will use for general purpose applications. Okay, whereas a controller is the one which is used for a single application or a specific application. Okay, so if you categorize the processors, we have 8086, 186, 286, 386, Intel processor i3. All these are the processors that you come across when you try to buy, when you look into the systems or desktops. Okay, so whereas if you go to a specific application, as I quoted the washing machine. Okay, so this washing machine doesn't have a processor, doesn't require a processor. Okay, why? Because its specific purpose is to wash. Okay, it is helpful in completing the task of washing. Okay, so for that alone, no need to buy a processor which is costing 5,000. So we can just go with a controller which is costing 500 rupees. Okay, so here cost also matters between the general purpose as well as the specific purpose. Okay, so that's the reason why all the embedded systems are built on controllers, not on the processors. Okay, so at the end of the day, the cost is the main thing which is going to come into picture. So all the time, okay, so whatever we are doing, all the trade-offs will end at M, that is money. Okay, so less cost we have to give, we have to spend, and we have to get maximum benefit of it. So all the embedded systems are concentrated only your microcontrollers. Okay, so these are the hardwares we are going to study from now onwards, right? So the basic microcontroller, okay, which is called as mother of all the microcontrollers, is 8051. Okay, so we'll start with that. Okay, we'll see some programming of it, and we'll try to convert this 8051 programming into a normal conventional program like C programming, okay, using a package called as embedded C. Okay, and then we'll improvise, or we'll go with the next type of controller like ARM controllers. Okay, then in the ARM controller, how we program it, how an embedded C will be used for programming it. So like this, we'll be going in day by day, right? So let us start with 805. Okay, so I hope no doubts are there in this. If anyone has any need any clarification, they can just drop a message, or they can ask. They are open to ask till now.
Any question from the students? As far as the fundamental basics are there, specific any query? Okay, sir. No problem.
Okay,
Move it. Yeah.
okay. So understanding that you have got the basics rightly, we'll start with this foundation uh, controller. Okay, so 8051 microcontroller. Okay, so this is introduced, or this is developed by Intel actually in 1980. Okay, only for this specific applications. Okay, and the architecture uh, is almost closely related to the industry standard. Okay, and the architecture is based on Harvard architecture. Okay, so what makes this 8051 different from 80 other processors? The processor will have only one memory block from where the code as well as the data has to be accessed. Okay, so when the code is being accessed, the data cannot be accessed. Okay, so this is the main problem which is having some speed issues in processors. Okay, so that has been countered in 8051. Okay, by separating uh, the program memory and data memory. Means two memories will be there. Okay, individual two memories, one memory dedicated completely for writing the code, and one memory to access the data. Okay, and that type of architecture we call that as an Harvard architecture. Okay, and this will improve the speed. Okay, so because simultaneously it can access the code, at the same time simultaneously it can access the data also, right? Then how about the computation? Okay, so computation means it requires it follows the computation method of CISC, means complex instruction set computing. Okay, so what is this complex instruction set computing? Okay, so complex variable length instruction, right? So if you see complex CISC instruction, okay, within one line we can perform more than one operation. Okay, so whereas if you take any other computation method, if you want to do a plus b whole square, okay, so here two operations are involved, isn't it? One is sum and one is the multiplication. So both can be done in a single line, okay, using CISC instruction set. Whereas there is one more instruction set called as reduced instruction set. Okay, so it will follow with it will reduce the complexity. Okay, but the operation will be done in the same fashion, just like a plus b whole square equal to a square plus 2ab plus b square. So if you see this, both will give the same result. Okay, whereas in a square plus 2ab plus b square, the number of operations are more. Okay, like multiplications are three multiplications we have, and two additions. Whereas a plus b whole square, it has only one multiplication and one uh, addition. Okay, so this operation, okay, so is introduced in a single line, a plus b whole square, and that single line we call it as CISC instruction set. Okay, so what happens with this single commands, the fastness will be further increased. Okay, now how, what does this CPU this 8051 architecture is made up of? Okay, so it doesn't have like 1 TB, all these things. Okay, it has certain features like the CPU is there. So the CPU, mainly the heart of the CPU is, we call it as ALU, that is arithmetic logic unit. Okay, and it can process 8-bit digital data. Okay, and we have an program counter for sequencing the instructions. Okay, and the internal memory, okay, the memory that is being fabricated on the 8051 chip has a size of 128 bytes. Okay, and 256 for the other variants. Okay, when it comes to the ROM, that is, we call it as a read only memory, otherwise we can call that as a program memory. Okay, so the size of this program memory is 4K. Okay, with on the chip, right? Whereas the RAM, we call it as a data memory, and its size is just 128 bytes. Okay, and further it can be increased for the other variants. Okay, right? This about the memory. Then it has four IO ports, bidirectional IO ports. We call them as P0, P1, P2, P3, port 0, port 1, port 2, port 3, through which we can connect the IO devices directly. Okay, or we can access any other peripheral using one of the port of that is associated with 8051. Okay, and then we have timers. Okay, so in order to give the timing constants, we have two 8-bit timers, two 16-bit timers, which can be used as four 8-bit timers. Okay, then we have some communication facility, serial communication facility, which provides a full duplex UART communication. Okay, for data exchange between the controller and any other device. Okay, or controller with other controller, right? And then it can handle 5 interrupts. Okay, so 5 interrupts, in which two are external. Okay, two are timer interrupts, and one is a serial interrupt. Okay, so these are about the architecture. All right, so now we go deep into the. I hope this slide is visible to you.
Yes, sir.
Yeah, fine. Sure that this slide is visible. Yeah, I hope now it is visible.
Yeah, it is visible, sir. No issue.
So now just we have seen the features of this 805. Okay, so what we have seen, so it has an ALU of size 8-bit. Okay, and it has the memory spaces like 4K of on-chip program memory, 128 bytes of on-chip data memory, and it has the other feature like the memory can be expanded externally. Okay, and the maximum memory that can be expanded external outside 8051 is 64 kilobytes of program and 64 kilobytes of data. Okay, and these four ports, port 0, port 1, port 2, and port 3, collectively has 32-bit bidirectional ports. We call them as, each port size is 8-bit again. Okay, and we have two timers, as I said, then full duplex UART mode, then 5 interrupt vector structures, for which we have 6 interrupt resources. Okay, and we have an on-chip clock oscillator. Right, if you see the pin description, okay, of 8051, okay, so this is the pin description where port 0, port 1, and port 2, port 3 are mentioned over here. If you see port 0, it starts from port 0.0 to port 0.7, and at the same time it can be used as address to data bus. Okay, so AD0 to AD7 it can be used, and when it comes to port 1, it is a pure IO port. Okay, so starting from P1.0 to P1.7, and then we have port number 2. Okay, so port 2.0 to 2.7, where the address bus will be alternative operation will be the address bus. Okay, and we have port 3, which is further used as a multiple port if you want to do the serial communication. Okay, so port 3.0 and 3.1 will be used as RSD and TXD pins. Okay, and if it is port if you want to use for accessing the external interrupts, then P3.2 and P3.3 will be used. And for timer, okay, we have timer 0 and timer 1 in timer inputs. Okay, so and then the last one is read and write stroke. So whenever the data has been exchanged between the memory and the controller, external memory, okay, the status will be reflected in this P3.6 and 3.7 as read or write. Okay, so then we have the power pins, which is VCC, and which is the 40th pin, and the ground is 20, along across which we will be connecting the power source, usually of 5 volts uh, power source, 5 volts DC power source. Okay, and we have an reset pin. Okay, so which will reset all the pins of 8051 to its initial conditions. Okay, so a small pulse can be given through the ninth pin, so which will reset all the statuses. Then then we have ALE, which is otherwise known as address latch enable. Okay, so when this is made as one, okay, all the address buses, that is from AD0 to AD6, AD15 lines will be used as pure address lines. Okay, if AL is 0, then AD0 to AD15 will be used as data bus from D0 to D7. Okay, means the data bus size is only 8 bit, whereas the address bus size is 16 bit. Okay, next we have EA, which is known as external enable pin. Okay, so whenever a external memory is connected to 8051, and if you want to enable that, then we can use the pin EA. Okay, so with active low. Okay, so by default it will be active high. Okay, so whenever it is made as active low, okay, so the external memory that is connected to 8051 will get activated. Then we have program store enable. Okay, so this pin is used for strobing the data between memory and 8051. Okay, so program store enable. So uh, uh, whenever we try to put the program, okay, and your 8051, okay, inside the memory chip of 8051, then we have to use this program store enable. So whenever we make this as active low, okay, so we can flash the program into 805. Okay, and then we have XTAL1 and XTAL2, through which we are giving a clock frequency of 11.09 megahertz for this 805. Okay, so typically the range of frequency that is given for 8051 is will be between 5 to 15 megahertz. Okay, and the block diagram. Okay, so this block diagram is the features what we have discussed. Okay, like 4K ROM, we will have 128 RAM, timer 0, timer 1. Okay, so then we have serial port, 4 IO ports, bus control, then oscilloscope, the oscillator to which we are giving the uh, clock frequency. Then we have the interrupt control. Okay, this is a simple block diagram. Yeah, so now this is the actual architecture. So once if you see your 805, and this will be the architecture inside this. Okay, but it is enough if you can understand this block diagram as of now.
Sorry for interrupt, sir. Can we take any interaction with the students? They understood this because some of them may be new because they are entering the third year first semester after second year. Okay.
Okay, okay, fine, sir.
So the first that particular 8051 that pins,
Yeah.
we can have some minor just questions with them. Have you understood what is this by students? Do you have any question regarding this particular one that you want to understand? Any particular label on this 8051? If there is no problem, then we can move forward. Means we'll take a feedback. Is it okay with you? Can we move for the block diagram after this particular slide? Okay. There are no questions. Did you understand that there are number of pins are there? Some of the pins for writing enable, reading enables. There are some of the pin for the interfacing, input and output pins. Okay. No problem. So the second slide is related to the block diagram. What actually the things happens as a ALU and all. So second slide, please.
Yeah. So this is your block diagram.
Okay. In this block diagram, anyone have any question? Because every basic fundamental things to be clear, so that if you are reaching to the ARM controller, you should not be in a mode of that asking the basic things what is that again. So you have to also prepare after the sessions every day, so you will get the better thing and you will get the real quality with understanding. So you have to also read at the home, that is necessary. Topics are known to you, it has been already been announced. So now it's 8051. If you study today after the session also, some queries will be there that can be discussed in the next session. So RAM, okay, read only memory, read access memory, the input output ports, serial ports, parallel ports, okay. So some interrupt specific controls. So this is the very much standard in the part of the any particular microcontroller. And what is the next slide is there? It is a bigger internal structure that we can say the structure of a heart. Okay. Yes, sir. Please. Third slide. Yeah.
So this is the in-depth architecture actually. Okay, so how these ports are connected. So is what are the serial interrupt uh, pins? Okay, parallel interrupt pins. All these things are exposed here. Okay, so as of now, no, not required for this. Now we'll see the main heart of the 8051, that is the memory organization. Okay, so as discussed, this 8051 memory architecture. Okay, so is on the chip we have certain memory, and off the chip, that is external to the chip, we have certain memory. Okay, so if you take the on the chip, we have two types of memories. One we call it as ROM, and other we call it as RAM. Okay, so ROM, usually it is called as program memory because it is just a read-only memory where we give actually our program. We keep our actual program. Okay, RAM is a data memory from where we access the certain several data. Okay, so if you see the program memory, so internally we have 4K initially, and then external we have 60K. So altogether put together we call it as 64 kilobytes. Okay, and in order to access this external 60K also, this EA pin that is present on the pin configuration, it has to be made as 1. So yeah, now if you are making external interrupt, that is EA as 0, then internal 4K will not be used, only the external. Yeah. So if you make EA as 1, okay, the internal 4K and externally for 60K will be used. So totally 64 kilobytes of program memory will be there with us. Okay, right. If EA is made 0, then all the 64 kilobytes will be accessed from the external. So no internal ROM will be used. Right. Now, if you come to data memory, okay, so data memory, otherwise we call that as RAM. Again, we have internal as well as external, but internally the size of the RAM is 128 bytes. Okay, along with that, we have certain SFR, we call them as special function registries. Okay, so which will be combined with this 128 bytes of data memory to access the data, right? And externally, if you see, we have 64 kilobytes of external RAM itself. Okay, so this is the memory structure of your read-only memory and write-only read-only memory and random access memory. Okay, otherwise program memory and data memory. Okay, so how it is used as external and how it can be used as internal. So whenever EA is 1, okay, your internal 4K of ROM as well as the external 60K will be used, and combinedly it forms 64K. When EA is 0, Okay, we have 64 kilobytes of memory only from external memory chip. Okay, this is about program. Okay, if you see the data memory, internally we have 128 bytes of RAM. Along with that, we have special function registry SFR we call it as. Okay, and we have externally we have 64 kilobytes of memory. Okay, so now if you see the internal RAM structure, okay, so they can be accessed directly or indirectly. Okay, so what are the things which can be accessed directly and indirectly? If you see the special function registry, we can access them by their direct addresses. Okay, whereas the internal RAM, it can be accessed directly or indirectly using some registers. Okay, now if you see the 128 bytes of RAM, so if you are clear with this, then we can go with the 128 bytes internal RAM organization. So this is very
Yes,
crucial
sir.
for programming actually. Yes. So any doubts? So if you don't have any doubts, we just go for the next this detailing of the 120 this RAM. Okay. I feel no questions. Okay. So see, this RAM is 128 bytes as we said, but still this RAM is further divided into three sections. Okay. So we call them as register banks. Okay. So register bank area we have, and we have bit addressable area, and we have one more area called as general purpose area. Okay, so what is this register bank? Register bank area is a composure of 8 registers 30 in four as four banks. Okay, like register bank 0, register bank 1, register bank 2, and register bank 3. Now what does this register bank consist of? Each and every register bank consists of registers right from R0 to R7. Each register size is 8 bits. Okay, so like this, if you see, we have four banks, register bank 0, 1, 2, 3. Okay, and each and every bank will have 8 registers with the same names. So R0, R1, R2, R3, R4, R5, R6, R7. The same set of registers will be present in bank 1 and bank 2 as well as in bank 3. Got it? Now, if I say, or if you want to program and we are just writing a program, we are just accessing a data from R0, then there will be a confusion that which R1 the 8051 will consider, whether the this first one or the fourth one. Okay, so by default, okay, always R0 of bank 0 will be selected. So whenever we mention as R0 or R1 or R2, okay, so they belong to register bank 0 itself. Okay, now for suppose if you want to use a register bank or register R2 from register bank 2, then how to select it? Okay, so one easiest way is select the register bank first and then use the name of the register. Okay, just like if you want to use R2 of register bank 2, first select the register bank 2 and then use the register R2 for further processing. So now if you see how we can select this register banks, we have 2 bits, okay, that is present in program status word of 8051. These are one more status register which is present in the CPU of the microcontroller 8051. Okay, so here we have 8 bits. Okay, so P is not to the parity, so we'll come to this bits when we dealing with the programming. Okay, so then there is a overflow, then RS0, RS1, F0, then AC and CY, and we have RS0 and RS1 bits which are called as register bank select bits. Okay, so register bank select bits like RS0, RS1. Now how to select this register banks? So simply if you make 0 and 0, register bank 0 will be selected. Okay, and if we make it as 0, 1, then register bank 1 will be selected. Then if we make, or if we provide it as 1 0. Okay, then bank 2 will be selected, and if you are providing 1 and 1, then register bank 3 will be selected. So if you want to use any register of say some register bank 3, then in the program status code we have to keep the status as 1 1, such that your register bank 3 will be selected, and then you can mention that as R5. So whenever you mention that as mentioning that as R5, immediately the register bank 3's R5 will be get selected. Okay, so you understood this, right? So 0 0 means register bank 0, 0 1 register bank 1, 1 0 register bank 2, on 1 1 it will come around register bank 3.
Understanding registered bank is important, students, because today we are directly doing the programming, but in the old days, while going to handle the microcontroller, we people has to find out the opcode sheets, understand the opcodes, then how the data is moving from one register to another register. If one instruction is we are going to execute, how much memory is required and how the switching of data is there. So this register bank and all the other things has very much fundamentals and very useful for every student to clear the things. Any doubt?
If
Nikhil?
your if anyone is hesitating to ask, you can just drop a message here if you have any doubt in the
Yeah.
chat box. Okay, so that can also be clear.
Yes, yes. You can put the message if in doubt is the students, no issue. But make it clear, please.
Sir, may
Okay,
I
sir.
ask you a question?
Yes, Saurav,
Yes.
right? You are saying
Yes, sir.
something?
Yeah. Sir, how the carry flags and the register banks are related to this?
See, carry flags here, the status register is the one, okay, which will store the status of the operations performed inside the ALU. Okay, now the register bank, okay, register banks are the data storage elements. Okay, so register banks, we have registers where the data will be stored. Okay, so if you want to select a particular register in which you want to store the data, then you need to select that register bank. So for suppose say, if I say you have to store the data in R6, okay, then there will be an ambiguity that which R6 we have to choose, since we have four registers here, R6, 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 isn't it? So now which register bank? By default, the microcontroller will always choose register bank 0. For suppose in that register bank in that R6, earlier a data was there which has to be used for further purpose. Okay, this microcontroller will overwrite the data. So in order to avoid that situation, okay, we need to select the register bank. Okay, so now R6 you can go with, since register bank 0 is occupied, register bank 1 you can utilize. So that can be selected by just putting the status as 0 and 1 for RS1 and RS0 respectively. So once you do that, okay, the CPU will CPU will select the register bank R0, register bank 1, and in that R6 will be used to store the data. Am I clear?
Okay. Yeah, yes, sir. Yes, sir. Means, sir, here, if you select the register bank 0, then RS0 and RS1 should be 00 for the first register bank. And then the registers associated with the register bank R0 to R7, then the different types of arithmetic and logical operations will be performed
Yes,
only on the registers based on the bank 0.
yes, exactly.
Okay, yes, sir. Thank you. Thank you, sir.
Fine. Yeah. So next, we'll go for the next. If you are clear with this, then we'll go for the next section. Okay. Yeah.
Yes, sir,
Then we
yes.
have then we have bit addressable area. Okay. So bit addressable area. So this bit addressable area is the area where you can process the bit operations. Okay. Now see, we say that your microprocessor is going to process the digital data. Microcontroller also process the digital data. But what's the big difference between a microcontroller and microprocessor is microcontroller always deals with the data in word pattern like bytes, okay, or word or double word, like 8 bit, 16 bit, or 32 bit. So for suppose if you want to operate only for 1 bit, okay, you might we have to do on the complete byte. The particular operation has to be done on complete byte. Okay, in order to change 1 bit status, all the 8 bits has to be disturbed. Okay, so again which will consume some time. Whereas in microcontroller, okay, it has a facility that only the bit sorry, only the bit which is intended that can be modified. Okay, so in that cases we require some memories where bits alone can be stored, means only one bit can be stored. Okay, so that for that we have a dedicated area in the RAM of 8051, which we call it as bit addressable area. Okay, and how many bit addressable areas are there is, so we have six, uh, 16 bytes. Okay, 16 into 8, totally 16 into 8 bits of bit addressable area we have. Okay, so next the rest is general purpose area where we can access the data directly. Okay, so put the data in the memory location, get the data from the memory location, like this. So this is the overall architecture of your RAM. So if you want to further divide the address locations, okay, so we can just make that as, so it starts from 00 to 7F 7FH. So this 7FH is, if you convert that into digital format, it is, sorry, into the decimal format, it is 127. So it starts from 00 location, 0 location, and it will end at 127, totally 128 RAM locations. Okay, we are seeing this register path. Then comes the special function register set above the RAM, right from 80 onwards. Okay, so there is your 80 up till 7F you have RAM. From 80 onwards we have a special function registers, okay, which are used for dedicated purposes, like if you want to access the timer. Okay, so the timer is there, so when we take a timer we require certain commands, like we need to start the timer, we need to stop the timer. Okay, and we need to know for how much duration the timer has to run. Okay, so all this information can be provided with the help of tcon, tmod, tl0, tl1, th0, and th1. Okay, these are called as timer registers, timer control registers. Tcon is known as timer control register, okay, which is used to control the operations of timer. Tmod register is the one which is used for selecting the mode of timers. Okay, and then TL1, TL0, and TH0 constitute timer 0. Okay, 16-bit timer 0 timer. Okay, and TL1 and TH1 constitute 16-bit timer as timer 1. Okay, so when it is, it can be further used as 8-bit time, sorry, 4 8-bit timers. Okay, then for performing the serial communication, we have SCON register, serial control register, and serial buffer register. In order to handle the interrupts, we have IE register and IP register. Okay, and in order to access the ports, okay, we have port 0, port 1, port 2, port 3 registers. Then we have data pointer, which is used as a pointer register to access the data from external memory. And then we have a power control register, which is somewhat closely related to the serial communication as well as the power consumption inside the 8051. Okay. Then we have stack pointer register for performing the stack registers. Okay, so each and every register, okay, is having its own address location. So we can call that port 0 directly in the programming, or with the help of the address of port 0 we can access that. So now how the address will be assigned. Okay, so the address is assigned as per this table. So it starts from 80 is the address location where P0 is present, then 81, which is stack pointer address, 82 is data pointer lower register, then 82, so 80, 81, 82, 83 is your data pointer higher. Okay, like this, and the three spaces are empty, and then we have tcon register whose address is 87. Okay, so whenever we are calling an address called as 98, okay, so 98, so corresponding to 98, which is there, we have ESCON register. Okay, so if you can see, this is like accessing that address with its name as well as its location, just like accessing the student with his name, okay, as well as with his USN number or your roll number. Okay, so this is how each and every register can be accessed in a 8050. Okay, apart from that, we have the program status load, which is located at D0 location, and two mathematical registers, we call them as accumulator and base register. Okay, so which are present at E0 and F0. Right, so yeah, so have you understood this? So how this RAM, okay, and your special function registers will are associated in 8051. So if you have any doubt, you can just clarify now itself. Fine, we'll go with the next thing. These are the pins operation. Okay, so we'll understand that later. Yeah, so we'll go with the timers. Okay, so quickly we'll finish this peripheral so that we can start our program. Okay, so first peripheral is timers. So as we said, we have two timers, timer 0 and timer 1, each of size 16 bit. Okay, further these timers are operated in different modes. Okay, so we call them as mode 0, mode 1, mode 2 and mode 3. Okay, whereas timer 1 will be operated in three modes: mode 0, mode 1 and mode 2. Okay, now how these timers are used? Okay, so it, when a timer is on, when the timer is off, so this is what the timer 0 operation. Okay, so let us say these are the times. So if the timer has to run, it requires, okay, and gate pin. Okay, so it requires a timer run bit which has to be on. Okay, right, and then we should have which timer we are going to use. Okay, so this timing operation, we can use the timing operation internally as well as externally. Means we can generate the time with the help of oscillator itself, okay, or with the help of external timer which is connected to 8051 through the pins T0 and T1. Okay, so now let us assume that there is a timer. Okay, so where TL and TH are there. Okay, once the timer completes its timing operation or the counting operation, okay, so your an interrupt will be generated. We call it as timer flag. Okay, now if this timer has to roll out, if it has to be run, then the gate that is present here has to be closed. If this gate has to be closed, okay, so if you see the logic, okay, so if this gate has to be closed, then the output of this NAND gate should be 1. Okay, so when this output of the NAND gate will be 1, when the inputs of this NAND gates both are high, then only the output of the AND gate is, sorry, not NAND gate, AND gate is 1. Okay, so then only the AND gate output is 1, then it closes the gate. So by default, the one input will be TR. This is called as timer run bit. Okay, we call that as starting bit of the timer. Okay, this should be 1, and the other input should be from either your gate or from the internal pin. Okay, interrupt pin. Okay, so this has to be 1. Either one of the inputs can be 1 or both the inputs can be 1. So that is this gate bit. Okay, so this gate bit is connected through a NOT gate. If it is 0, right, then since it is passing through the NOT gate, the output will be 1. So the input for this OR gate will be 1, and by default the input other input of the AND gate will be 1. Okay, so for suppose the gate input is 1, okay, then uh, the input for your OR gate will be 0. Okay, and since one bit is 0, the other bit has to be 1, which we are getting from internal interrupt pin. Okay, So for through the interrupt pin also we can run the timer. Okay, so this is how the gate is controlled with this 3 bits: TR, gate and interrupt pin. Okay, now what type of events we have to count, whether it is an internally generated clock pulses we have to count, or externally generated clock pulses we have to count. Okay, so if you want to count the internally generated events or clock pulses, then that is known as timing operation. Okay, so this timing operation will take the clock pulses directly from the oscillator which is connected to your to our 8051. For suppose if we have the events which are through the external pin, then that operation we call it as a counting operation. Okay, and for this C by T bar bit, okay, should be kept as 1. Okay, so once it is kept as 1, this switch is going to connect to this TP, okay, through which we are going to give the clock pulses. Okay, and these clock pulses are given to timer when the gate is closed. So the timer is going to complete the timer operation once it is rolling out from zeros to 1. So from all ones to zeros, okay, the timer flag is going to be set. Okay, so means stating that the timing operation is completed. So this is the overall operation of a timer. Okay, now if you take your timer 0, so the pins will be all the same. The only difference is here we will be having timer 0 pin, timer run 0 pin, then external interrupt pin 0. Okay, if it is timer 1, we will be having 1 1 1 here. Okay, now come to the modes of operation. Okay, so mode 0, even though we have the size of the timer is 16 bit, okay, this 16-bit timer can be used in different modes. If you take mode 0, right, so it is used as 13-bit timer. Okay, so 13-bit timer means 8 bits from the higher and 5 bits from the lower. Okay, so the maximum count that is possible is 1 triple FH. Then mode 1 is a pure 16-bit timer. Okay, so where 8 bits of timer lower and timer higher will be used. Okay, and timer flag 0 will be used as an interrupt. So the maximum count will be all ones, all 16-bit ones. Okay, in hexadecimal we call it as FFFFH. And if you take your mode number 2, which we called as auto reload mode. Okay, auto reload mode, best example is for every 60 seconds we count it as 1 minute. Okay, so this 60 seconds are loaded in timer 0. Okay, and once the timer flag is rolled off, when the timer is rolled off, all the 60 events are counted. 1 minute is given as an interrupt. Okay, and again the same 60 seconds, okay, will be loaded into your timer 0, and again it will be rolled off. So repetitive work. Okay, repetitive counting, repetition of same counting with auto reload. Okay, it's called as mode number 2. It is actually an 8-bit timer, okay, with auto reload. Then we have mode 3, okay, so which is used to generate serial communication interrupts. Okay, so we have baud rate, right? So if you, whenever we call it as serial communication, the baud rate is given as 100 Mbps, 20 Mbps, like this. Okay, so this baud rate is given through, is generated through timer 0. Okay, okay, and the interrupt is given through timer 1. This we called as timer mode 3. Okay, when it comes to timer 1, okay, mode 0, mode 1, okay, mode 0, mode 1, and mode 2 will be the same thing, and mode 3 will not be present. Okay, now whatever the pins we have seen in this logic, uh, all the bits are present in timer mode register. Okay, where gate, C by T bar bit, M1, M2, we have seen this four gate and C by T bar in the control logic of this. So here we have gate and we have C by T bar bit, which will choose between timing and counting operation, and gate is a bit which is used to open or close, control the gate operation. Okay, then M0, M1 are the bits which are used to select the mode of timers. Now if you say your TMOD register, 4 bits are repeated from LSB to MSB. The first 4 bits, okay, are dedicated for timer 0, and next 4 bits are dedicated for timer 1 individually. Okay, Then we have flags like run bit and stop bit. Okay, timer run bit and timer stop bit. So timer run bits and timer stop bits are present in TCON register. Okay, so right from here, if you see timer flag 1, okay, which is a stop bit for timer 1, timer run bit 1. Okay, so this is the run bit for timer 1. TF0, timer flag 0 for timer 0, TR1 for timer 0, then external interrupt bit 1. Okay, external timer bit 1. Okay, this is the interrupt pin. Okay, then external interrupt 0 and external interrupt 0 flag. Okay, so the whenever the timer is done with the of external operation, that is counting operation, then we can use our e IE1, IE0. Okay, for that the corresponding interrupts will be IT1 and IT0. Okay, so these are timers and these are interrupts. Next, coming to the serial communication. Okay, so serial communication is a full duplex mode. Okay, so full duplex mode means simultaneously we can perform the transmission and receiving operation. Okay, so in order to perform this, okay, we have serial buffer register. Okay, one buffer register connected to receiver and the other buffer register which is connected to the transmitter. Okay, so transmitter control and receive control will have the SBUF register. Okay, and these are controlled with TXD and RXD pins, right? Then just like in our timers, for serial communication also we have different modes. Okay, so we have mode number 0. Okay, so like where 8 bits are transmitted or received at a time at a baud rate of f into 1 by 12. F in the sense the frequency of oscillation of 8051, that is 11.09 divided by 12, that will be the baud rate. Okay, now if you see your mode 1, okay, so this mode 1 is an same as of your mode 0. The only difference is it will have the variable baud rate. Okay, so this variable baud rate is generated by timer 1. Okay, then mode 2. Okay, so we have all the mode 0 and mode 1 is a serial communication which will perform 8-bit operation, whereas in mode 2 and mode 3 or 9-bit operations we call them as. Okay, where the 9th bit will be transmitted through your SCON register, right? So the data number of data bits will be 9 here. Okay, and the baud rate for mode 2 will be f by 32 or f by 64. Okay, and if it is mode number 3, okay, the same 9th bit transmission with a variable baud rate. The variable baud rate again it is generated through the timer 1 overflow rate. Now these are the two registers, okay, which are responsible for our serial communication. Okay, so SM0, SM1 will select the mode of operation 0, 0, 0, 1, 1, 0, okay, and 1, 1. Mode 0, mode 1, mode 2, and mode 3. Now SM2, okay, so SM2 is known to be the is used for the 9th bit transmission. Okay, so usually if you take 8051 microcontroller, the size of the microcontroller is 8 bits only. Okay, but if you try to transmit 9 bits, the 9th bit has to be located somewhere, isn't it? That 9th bit, that location is known to be your SM2. Okay, and by default your controller will do the uh, transmission. Okay, whereas the receiving is possible only once it is reset. Okay, so first one packet is received. Okay, after for receiving the second packet, this we have to enable this REL. Okay, at the same time we have to clear the interrupt RI. Okay, so this SCON register will have the modes. Okay, receive enable bit. Okay, and then TV8 and RB8 bits. Okay, TV8 and RB8 means uh, whenever the 8 bit is transmitted, whether the interrupt has to be generated for the rising edge or falling edge. Okay, so that is decided with the help of RB8 and TB8. So if you are making it as 1, okay, it is for rising edge. Okay, means whenever the 8 bit is started to transmit, okay, then TI will be generated. If it is for falling edge, we can make this as 0. Okay, so after during the falling edge of the transmission bit of 8 bit, your TI will be active. Okay, and holds good for the same thing for receiving also. Then we have PCON register. Okay, so as I said, this is closely associated with your SCON register also. Okay, why? Because uh, the baud rate whatever we are defined through SCON can be, sometimes we can increase it, we can maximize it, or we can double it with the help of SMOD bit. Okay, so if whenever you keep one, okay, whatever the baud rate you have defined through mode 0 or mode 1 or mode 2 or mode 3, that baud rate will be simply doubled. Okay, right. So this is about the serial communication bits. So any doubts in this serial communication port or timers?
Hello, sir.
Yes, sir.
Sir, how do we make the control register for the S1 or P1 registers for any example?
Saurav, can you be little bit clear? Your voice is breaking.
Yeah, sir. Actually, if we want to use the S1 and P1 registers
Okay.
during the program, then
Hmm.
sir, how do we define the control word for such registers?
Yeah, that is what. Say, if you want to configure SCON register, let us say, if you want to use mode 0, okay. Mode 0 means what should be the configuration? Here, the status should be 0, 0. Yes, SM0 should be 0, SM1 should be 0, okay. And imagine that you are going to enable receiving also, right? So now SM2 will be 0, right? So 3 bits. So here it will be 0. Let me see. Yeah. So here it will be 0. Here it will be 0. Since you are using mode number 0, here it is 0. You have to receive the, suppose that you want to receive the data also. Then you can just make it as 1. Okay. And let us say by default at the starting edge, the rising edge only you are going to have this 0, 0, and this TA and RI are generated one. Okay, these cannot be programmed. These are automatically set and reset by the program. Okay, so we have to leave as such. So the default condition will be 0, 0. So now if you just see this control word, okay, so whenever you transfer a data called as 1, 0, H, okay, to the SCON register, okay, your serial communication will be using a mode called 0, okay, which supports 8-bit transmission at a baud rate of f by 12. Okay, so that will be the baud rate. Okay, and it has the ability to receive the data also, right? Now how this is being generated, right? So once the 8-bit is being transmitted or received, you are going to receive a transmission interrupt or receive interrupt. So once one packet of data means 8 bits with a start bit and stop bit. So when this packet is received or transmitted, okay, your, let us say, first transmission scenario. So TA will be set to 1 automatically, and then what we need to do is, using the program, we have to clear this bit to 0 again, so that the next packet can be transmitted. Okay, now we have used the baud. What is the baud rate we have configured? So we have configured the baud rate as f by 12, right? And we don't want this baud rate, we want to speed up this. Then go to PCON register, set it as 1. Okay, so immediately this will be doubled. So it will be doubled in the sense the baud rate will be defined by f by 6. Okay, so this is how we configure it, and we have configuration words are being sent to the registers. Okay, and the command what we will be using will be move. Okay, scon comma 10 10H. Simple. I think I'm clear with this now.
Yes, sir.
Yeah,
Yes, sir.
fine. So quickly, yeah. So since it is done, okay. So we'll go with the next peripheral, which is called as interrupts. Okay. So as discussed, these interrupts are five interrupts. Two are external, two are timer. Okay, one is serial communication interrupt. Okay, so for serial communication, we can have either transmission interrupt or receive interrupt. That's why we call it as six sources. Whereas where the vectors are just five. Okay, so five vectors like serial vector. Okay, external interrupt vector and timer uh, vector. Okay, from this we have six sources, right? So these interrupts can be masked or unmasked. Masked in the sense, if you want to process that interrupt, you can process it straight away whenever they are occurring. If you don't want to process it, okay, even if it is generated, simply you can make it as zero. So that process we call it as masking. Okay, and this process can be done with the help of two registers by the name called interrupt enable register and interrupt priority registers. Okay, so now if you see this, so external interrupts like external interrupt 0, external interrupt 1, these are the interrupt sources. Then we have timer 0, okay, then timer 1, then we have serial communication either one. So that's why an OR gate is there here for you. So these are called as interrupt resources. Okay, so if any of the interrupt has to be processed, any one of these interrupt has to be processed, there will be a bit called as EA bit, global bit we call it as. If this global bit is 1, then only any one of the bit can be processed. Okay, if your EA bit is 0, okay, then any of the interrupt which is uh, generated, that cannot be processed. Okay, and coming to the interrupt priorities, sir, what happens if two interrupts are generated at a time? Okay, so at a time, if it is generated, it will go with the priority, okay, that is already assigned. So the priority goes like this. Okay, the priority, the first highest priority is given for the external interrupt 0. Okay, then next interrupt is given for timer 0, next external interrupt 1, then timer interrupt 1, and the least priority is given to serial communication. Okay, so then this is the global enabling process. Now individually also we can enable and disable it. Okay, so this is done with the help of your IP and IE registers. So IE register, interrupt enable register, which will enable or disable the interrupts. Okay, all the interrupts also at a time. Okay, and then we have the priority register, which will assign the priorities to individual registers. Okay, so now let us see what is this interrupt enable register. If you see the interrupt enable register, we have EA. Okay, so if this is kept as 0, all the interrupts, okay, which are generated will not be processed. If it is 1, then only we have the option, okay, then only the 8051 has an liberty to execute the interrupts. Okay, so for suppose if you don't want to process the interrupt of timer 1, then simply you can make this as 0. Like if you make this as 0, even though the timer 1 is generating the interrupt, okay, that will not be processed. So the default condition is EA should be 1, and this can be anything, either 0 or 1, like this. Okay, so if it is 1, it will be it will be processed. If it is 0, it will not be processed. Okay, then comes IP register, where the priorities are given. Okay, so the default priority will be from external interrupt 0, timer 0, external interrupt 1, timer 1, and then your serial communication. Okay, so if you are putting it as 1 1, okay, so it means two interrupts are being generated or two interrupts are processed, out of which the highest priority is given for timer 1 and the least priority is given for serial communication. So the priority will go from right to left. So here will be the highest one and this will be the least priority. Okay, so this is how the priority is. Okay, so highest priority is given for the external interrupt, the least priority is given for serial communication. Okay, so all the interrupts we can see in the TCON register. So if you have any doubt, you can just go ahead. Otherwise, we'll start the programming directly.
Yes, students, now the fundamentals are clear about 8051. Can you start with the programming? Any question? Specifically from third year students or final year students, those are appearing now for the same. Okay, sir, start with the program, no issue.
You just go ahead.
Yeah.
Right. Say the programming we'll start with an ALP and then we'll just convert this ALP into an embedded program. Okay, so this is how the flow will go. Right. So this coming to this programming of 8051, okay, or programming of any hardware, it is not a straight program. Okay, so there are different types of programming languages like high level language programming, low level language programming. Okay, like this. So if you see the high level programming, okay, so your C language, C++, okay, all this comes under high level language programming. Then low level language programming, which is known as a language which directly interacts with the hardware. Okay, so a language that is directly interacted with the hardware is zeros and ones only. Okay, so this zeros and ones, again we can't write the program for using zeros and ones. Okay, so these zeros and ones are kept in a separate some keywords. Okay, and these keywords will be used to execute that program. Suppose if you want to do addition of a plus b, then the plus operator will have a separate keyword. Okay, this keyword is a program, okay, which will make a and b to get added up and the result to store in some register. Okay, the keywords what we call, okay, this composure of these keywords we call them as assembly language program. Okay, so this assembly language programming have a set of unique set of rules and regulations. Okay, so if you want to perform some data operations, data processing operations, we have certain instructions, certain keywords. Okay, if you want to use how the data has to be accessed, okay, from memory or into the, if you want to take the data from the memory or if you want to put the data into the memory. Okay, so the way in which the data is to be handled, so for that we call them as addressing modes. Okay, then how the data has to be moved, okay, that is along with the addressing modes. With the help of data transfer instructions we will be checking, and then program flow instructions. Okay, so how the program flow can be controlled. So usually what happens, the assembly language programming is an sequential language, means line by line language. Okay, after executing first line, the second line will be executed, third line, fourth line, like this sequentially it will go. Whereas if you see the high level language, we have jumping structures. Okay, we can use some functions. Okay, we can use some while loops, we can use some if loops. Okay, so these are by which we can control the program flow. Okay, so the program flow is random in high level language, whereas in the ALP, okay, it is a sequential language. Okay, sequential, right? So in order to control that sequence, okay, what are the instructions we can have, so that we are going to see here. So now if you see the, first I'll start with the addressing modes. Okay, So what is an addressing mode? As I said, the way in which the data for the 8051, okay, or a particular processor is handled, we call it as addressing modes. Okay, right? So if we have a data directly, and if the data has to be moved to any one of the register, okay, then it is called as immediate addressing mode. Okay, and the data is specified with an operator called as ash. Okay, so if you are not putting it as ash, then the 0 is considered as a simple memory location. Okay, so this is how we will write the immediate addressing. Now next comes, so the register addressing. Suppose the data is present in one register, that data has to be transferred to one more register. Okay, then the data is transferred between two registers. So that type of data movement, we call it as register addressing mode. Okay, I'm telling you in a very simple way, right? So, so if you want technically, right, this, then we have to call this as operands. Okay, so this is an instruction, this is an operand. Okay, so this is a destination operand, this is a source operand. So the data from source operand will be moved to destination operand, and if both the operands are registers, we call that as a register addressing. Okay, so this is what the register addressing, right? And from move r7 comma r4 comma r7 means the data movement cannot be done directly, means from register to register, from the general purpose register to another general purpose register, we can't do it. Okay, so always the data processing has to be gone through the mathematical registers only. Okay, right. Next is direct. Okay, so if you know the memory location, so as I said, when we are discussing about the RAM architecture and the special function registry, okay, the special function registers can be accessed with their names as well as their locations. Okay, so at the same time you have the general purpose area where the data can be kept. Okay, so these uh, locations can be accessed directly with their location, okay, or with the name, right? So just for example, so if you are using general purpose registers R0, okay, R0, if you take the register bank 0, R0 of register bank 0, the address is 00. So whenever we are writing it as move a comma 00h, okay, so by default the data that is present in 00 location or R0 location will be moved to A. Okay, so two ways we can write it. Okay, so instead of writing the name, if you write the location, it is called as direct memory addressing mode. Okay, so now if you see like this, the general purpose register can be accessed at the same time that your general purpose memory area also can be accessed. Okay, along with that we can use the special function registers also. Okay, so if you see the special function registers, we can access them direct only with the direct addressing only, so not with indirect addressing. Okay, next is register indirect addressing. Okay, register indirect addressing where the memory location will be stored in one register. Okay, and that register in that register in that memory location, if you want to do any changes with the help of that pointer register, we can do that. Okay, just like this here, if you see, uh, we have taken a PSW to where we are moving 0. Okay, means register bank 0 is used. Okay, and we are trying to move the data called as 3C into R0. Okay, and move at R0 comma 3. Now this 3 is your data. Okay, this 3 data is moved to an R0. Okay, in that R0 at R0, R0 at R0 means inside R0 what is having 0 3C. Now this 3C is considered as a memory location, so into that memory location, so 3C is pointed by R0, So the memory location pointed by R0 is loaded with a value as 3. Okay, whereas R0 value is again 3C only. Okay, so now this R0 is indirectly accessing the memory location 3C so that the data can be sent. Okay, so this is how your register indirects will be used. Okay, for suppose if you want to use the data or the locations which are present outside the microcontroller, then outside the microcontroller the space is huge. Okay, so huge means the size of the address locations are also different. Okay, instead of 8 bits we have 16 bit, isn't it? So this 16 bit, in order to access or in order to store the 16-bit address location, we have a register called as DPTR, data pointer. Now just see the difference here. Here we have 3C, okay, which is an 8-bit memory address location, whereas 900H is a 16-bit address location. Okay, so which can be handled only by DPTR. No other register can handle this 9000H because all the sizes of the registers are 8 bits only. Okay. So now this data operations we'll see with the help of a simple simulation. Okay. So what I'm doing, I'm just passing this. Yeah, please confirm me whether my window is shared or not. I think my window is shared.
Yeah, yes, sir. Visible, no issue.
See, this is a simple interactive 8051 tool, okay, where we can learn the programming of 8051 very easy. Okay, so this is called as SIM51. Okay, so this I'm using for ALP. Okay, for embedded C we'll be using the key C. So what we are doing in this due course of time is we are going to learn parallelly the ALP programming as well as embedded C programming. Okay, so for embedded C by default the tool what we use is key. Okay, only for one or two we'll be changing that. Rest everything we are using key level. Right. Now see here, there is a console where it shows all the 8051 programming model. Okay, so now if you see the data memory, it is extending from 00 to 7F. Okay, this is your RAM. Okay, and we have your SBUF register, we have timer register, we have registers R0 to R7, we have registers by uh, accumulator, base register, PSW, IP register, IE register, PCON, data pointer, SP. Okay, and the status of PSW, everything we have here. Okay, so the system clock pulse is 12 megahertz by default we can keep, and if you want to update the frequency, we can update the frequency to say some thousand like that. Now let us say we are going to transfer a data to 70H. So first we can write it as move. MOV is an instruction for data transfer. Okay, A comma hash 00H. Okay, let us say 04H I'm doing it. Then this data I will move to a location called 17H comma E, right, and heart. Now you can run this program. What I try to do is we have taken a data called as 04. Okay, so first this data is first transferred to accumulator register. From that accumulator register, we are transferring this data, copying this data to a location called 70H. Okay, now let us see how we will run it. Okay, so we can run by intervals. Okay, now see. this is how we run it, right? So after running, okay, if you want to see stepwise, so I'll run stepwise. Okay, let's reset it. Update the frequency to 1. Okay, so once it is assembled, so once you press assemble, right, so if any error is there, it will show the error. If no error is there, okay, we'll have a message called as no errors are there, right? Then stepwise. So what's the first instruction? First we are moving 4 to A register, isn't it? 4. Okay, so now see here, 4 is moved to accumulator register, right? So in your A register you have 04. Next, the next step what we are doing, the same contents of A, the contents of A is simply moved to a location called 70H. Now we have the data memory here, right from here 00 to 7F. Okay, so now next step, now see here, this 04 is moved to 70 location. Now we try to uh, move this data to some other location, let us say 65H, comma 70H. Now let us see memory to memory whether it is possible or not. So if you see, right, no errors are there. Now stepwise, 1 is there. Next step, now 65 location. Now see here, 65th location. 60 is this, 61, 62, 3, 4, 5. So your 04 is being loaded here. Okay, so directly from memory to memory, we have done it. Okay, now one more type of data transfer we do it. Okay, so let us say move R0, comma, hash, let us say 0 or 30H, I'm taking. Okay, so now let us see how it is going to happen. So we are assembling it. Okay, so once it is assembled, we got no errors. So first step 04. Okay, the second step A is moved to 4, so 70. Next step 65 is moved to this move, and then next to see what is happening to R0 register. Okay, yeah. So now see your R0 register is loaded with 30H. Okay, so now this 30H we can convert that into a memory location. Okay, so in 30H what we are having, we are having 00. Okay, so now what we do is move B, comma, at A. Okay, so at R0, let us say, or make it as A only. Okay, so what we are doing, so whatever the data that is present in 30H, okay, so 30H is 00, so that 00 we are moving it to a register called as A. Okay, so earlier A was 04, then after executing this code, your A value should be 00. So now this is where we are doing. So R0 is loaded with value called as 30. Okay, now in the next instruction here, okay, move A comma at R0. R0 is 30. So at 30, whatever the value is there, that is moved to a register called A. So at 30, what we have 00, isn't it? So that 00 will be moved to accumulator register after executing this instruction. Okay. So now let us check this. So now your R0, is having an unknown label. So we'll just replace this with move I have not used R now. Move a comma at R, right? So now I have assembled it. So have you seen the error? What was the error? The error, instead of 0 I have typed O. Okay, so now see, so what is happening? So I'll give a new data. I'll reset it. Every time if it is 4 now, so I'll make it as 6 0 70. Okay, so now let us see. Let us run the program one by one, stepwise. So first accumulator is moved to A register, then A is moved to 70. Okay, so 70. So then 70 is moved to 65. We have to upgrade the frequency to 100, let us say. Then step. So now your 30H. Okay, so now your control is here. R0 is 30. So the R0 is 30. Now once by the time we execute this, okay, your accumulator is cleared. So whatever the value that was there in 30, it was moved to accumulator. Now let us see this, like move R1 comma, let us say R0 comma A, 30H comma R0. Okay, so A we are moving to 30H. Okay, and then in that whatever the value that is present in R0, we are going to increment at 30H. So it is not possible. So what I'll do, R0 comma 30H. So 30H. Okay. Now let us see how the data is being changed. Okay. First, we have taken accumulator is loaded with 6. Okay. Accumulator is loaded with the value called 6. Then 70, we are loading with 70 location 6. Then 65 is loaded with 6. Okay. Then your A value is moved to R0. R0 is 30. Okay. Earlier. So R0 is 30. So A is moved to R0. Then increment 30. So what at 30 now at R0. R0 is R0 value was 30. Okay, so the value that is present in 30H has been incremented by 1. Okay, then you are moving that value to accumulator register. So at the starting of the program, accumulator was 06, whereas at the ending of the program, the accumulator is updated with 1. Now, this is how, with the help of addressing modes and data instructions, data transfer instructions, and data manipulation instructions, we can program your 8051. Okay, this is about only the data transfer. So you have seen how the data is moved between your general purpose registers, okay, and special function registers like this. Now, can we do this? Move R0 comma R7. So when we are discussing the theory, we came across that this is not possible. Now let us see whether it is possible or not. So now see, immediately it is throwing an error as R7 cannot be used here. So now let us see. Yeah, I'll use some other register. Let us say R4 comma R1. Whether this is possible. Again, it will be error. Means so the data cannot be transferred between two registers at a time. Okay, at a time in the sense both the registers cannot be general purpose register. Instead, what we can do, we can transfer the data of A here, then move this data to R7. So A to R7 or R4. A comma R4. Then here R7 comma. So now R4 value was 0, right? So now here what I will do, I'll just add one more line. Move R4 comma say from 0 34h. Okay, so now this data run, just concentrate only on these three blocks because all the other lines we have checked it. Okay. Six, then A70, then 70, then R0 is 6, 30 it has been opened, then 31. Now earlier the data was 1 and 1, now it has incremented to 2. Okay, now R4, so R4 is loaded with 34. Okay, now this R4 value R4 is moved to A. So now R4 is moved to 34. Okay, and this 34 has to be moved to R7 register. So now see. So now R4 and R7 has the same values, but directly we can't move. With the help of accumulator register only it is possible to move. Right? Yeah. So in the data transfer instructions, if you have any doubt, you can just write now.
Hello, sir.
Sir, hello. Yeah.
So, what is the role of the update frequency in the simulator?
Which one?
Update frequency.
The
Yes, sir.
frequency,
This one.
update frequency is the time required to execute one instruction. Suppose if I am putting it as 1, right? So after 1 second only you can see the result. Okay. So see how much delay will be there. Okay. After 1 second only this assembling everything will be done. Step. Okay, like this. If suppose I am increasing the frequency to 5000, it will be done at the faster. That's all. Very fast. Immediately the steps can be, you can see the steps how it is moved. Okay, so this is about the updated frequency. So higher the frequency, sometimes what happens, if you put a higher frequency, at a higher rate it will be moved, where you will be missing the data transfer. Okay, so always the optimal frequency will be some 10,000 hertz, that is 10 kilohertz or 1 kilohertz. I prefer 1K. Yeah. So any other doubt for